Hi guys, so welcome to lesson 2 of our third week, hopefully our last week. We'll have to wait and see what comes out in the next couple of days, but we're going to keep motoring on. We're going to correct those questions from Tuesday and do something new, back to a bit of chemistry, some atomic theory which you would have started last year, atoms and that, and then we'll just have a quick revision of that. And then next week we'll go into bonding. We'll just do about half an hour's worth, and there'll be no homework today. The homework is just what I gave you on Tuesday, as agreed. So we'll go and do that. Thanks for everyone who tuned in on Tuesday and the live lesson. We'll do another live lesson on Tuesday coming. So one live on Tuesdays and this video on Thursdays. Okay, right. So we go back to the one and have a look at those questions. Okay. So here we are, we're still in this chemical reactions folder for the moment. I've added a new folder, in there called atom periodic table and bonding. But we'll stick with our chemical reaction, these exam questions for now. Okay, so I asked you to do these, we'll fill the answers to some of these. So you're asked to put in 1, 2, 3 and 4 into these ones. So well, the obvious one is number 3, which is precipitation. So that's going to be that's going to be number 3. Heat from the sun converts liquid water into water vapor. So that's here. It's going to be number 1. Plant lose water through transpiration. So here's the plant losing the water through transpiration, which is number 4. Not to be confused with the carbon cycle, which is going the opposite direction. Okay, so be careful there. And the last one is air currents. So your air currents are up here in number 2. Okay. And in 2018, Ireland experienced low rainfall throughout the year. Okay. This led to water shortages and restrictions on water use. Describe one way in which water usage in a home could be reduced. Now, I don't want you to get all clever on this. Go basic, go simple, and you'll see I've put the answers down the bottom of this. Not all of them came out, but most of them did. And you'll see they take pretty much anything. So don't overcomplicate it. So one ways in which water usage in a home could be reduced. So things like short showers instead of baths. Uses less water. Uses less water. Not using your hose to water your garden would use less water. Washing your dishes in the sink as opposed to washing in the dishwasher would probably use less water. So there's loads of ways of storing water, but be careful. They say one way. You do yourself out of the marks by listing a load of them. Describe one way. Okay. That's not bad for 15 marks for a question. We take that. Another one on the carbon cycle. So we have in here, we have W, X, Y, and Z to fill in. And we also have 3 words we can chuck in: respiration, photosynthesis, and combustion. So what do they ask us to do? In the table below, write the name of each process. So W is going from coal up to the atmosphere. So that's going to be combustion, so burning something. Combustion. X is going to be going from the tree up here. So that's going to be respiration. The proper term really there should be transpiration, but we go with respiration because it's definitely not this one, going from the atmosphere down to the actual plant. And that one is going to be photosynthesis. The plant taking in carbon dioxide to make its own food. And Z is going to be going from the animal up to the plants. We only have, it's not photosynthesis. Animals don't photosynthesize. It's not combustion because we're not burning the rabbit. It's respiration as well. So plants and animals respire. It's just usually when we talk about plants, we don't say respiration, we usually say transpiration. Okay. And then, in 1800, the population was about 1 billion. 200 years later, the human population is more than 7 billion. Humans have both positive and negative impacts. 2 areas of human activity that affected the environment negatively. Okay, well, two areas of human. What the main one is burning fossil fuels. That's FF. Burning fossil fuels is a main is a really bad way of putting loads of carbon dioxide and affecting the environment, climate change, global warming, the whole lot. The other way, and related, is cutting down trees. If we want to get fancy about it, deforestation is a bad way, is one thing we've done it. And there's a few of those. Explain how one of the areas you've identified has a negative impact. So if we take either of them really. Burning fossil fuels, what that does is extra carbon dioxide is released into atmosphere. I'm just keeping it. Okay. Two areas of human activity that affect the environment positively. Okay, we could just go the opposite, I suppose. So we could say anything like green energy, like putting in solar panels and wind energy. So using green energy, you could even write things like electric cars, things like that. And the other one, I mean, there's so many, biodegradable coffee cups, the reduction in plastic bottles, or keep it simple, planting more trees. And you'll see in the answers, they pretty much take anything good there for that. So it's quite difficult to get that wrong. Explain how one of the areas identified has a positive impact. Okay, so if we take the green energy one, so green energy one means less burning of fossil fuels, which means less CO2 released. Okay. Right, onwards. This is another one, and these are all just random ones taken from different years off exam papers in junior cert. So this is global warming. So you have a picture here of the planet melting, essentially. How can human activity give rise to global warming? So basically more, same thing. So we're going to start repeating ourselves. More CO2 released into the atmosphere. One effect of global warming. So actual effect, how do we feel global warming? So you could say more storms. You could say it gives rise to tsunamis. You could say, the first one that comes into my mind is rising sea levels. Rising sea levels. So there's lots of them. Again, don't try to overcomplicate these. Okay, onwards. 4 methods of waste management. Things like composting, compost bins, incineration, landfill, and recycling. Okay, so you can pick any two. It doesn't really matter. And I tell you, I won't even do them. If we were to pick composting is putting all your biodegradable stuff in a bin and it turns back into compost, so it turns back into soil. So if I put composting here and how it works, biodegradable material breaks down and becomes compost. Incineration is, so I can put incineration here, and I could say it's just burning waste. So incinerate something is just to burn it up, put it in a big huge tank and burn it. Landfill, if I was to pick landfill, I would write about just getting the waste, sticking it in a hole and burying it. And that's where a lot of our black bin waste goes to, or grey bin, as some people call it. It's just putting it in and burying it. It doesn't ask you, is it good or is it bad, or is it just asks you, what's the name of it? How does it work? And recycling is going to be your last one, and that is reusing. So that is turning it into a new product. So your paper that that your takeaway comes in is probably been paper before, because it's been recycled. So keep it nice and simple. Okay. This photograph of Earth was taken by a member of Apollo 17. 2 ways in which we can care for our planet. Okay, same thing again. 2 ways that you can care for our planet. Go for the not burning of the fossil fuels, the promoting green energy, to keep an eye on our carbon footprint, to reduce, reuse, recycle. Any 2 there. Keep it nice and simple. There's no point writing them out again for you. Now, this one, and I can often throw this in as a graph. So that's about 2 years ago. The increase in carbon dioxide. So basically what they've done is they've given us a graph and they said, right, here was the carbon dioxide in the atmosphere in 1960. Whereas up here in 2010, you're right up here at 380. That's in parts per million. 380 parts per million. So we went right down here from something like 315 parts per million, all the way up here to about 385 parts per million. So it's increased all the time. You can see in this little graph down here, they're showing you that in April, it goes up like that. In October, it goes down like this. It goes right down the end there. So it's dropping for some reason in the winter months, and then it starts to rise again for the summer months. Okay. Explain how either the use of fossil fuels or deforestation could have contributed to the increase. So we picked those before. So your explanation is, so we picked deforestation. Deforestation is less trees, means less CO2 taken from the environment, from the atmosphere. So remember, trees take it in. So if we cut down trees, there's less trees to take in this carbon dioxide. I could pick the use of fossil fuels, and my answer would be that there's more carbon dioxide being pumped into the atmosphere because we're using combustion to burn these fossil fuels, releasing carbon dioxide. One possible effect of continued increase in carbon dioxide on the Earth's atmosphere, so same as before, rising sea levels. So I'm going to stick with that. There's an overall increase in carbon dioxide. There is an annual rise and fall, as shown in the box in the diagram. So we're talking about this little small one here now. Why would carbon dioxide decrease between April and October of each year? So why is carbon dioxide concentration increasing between April and October? Well, April and October, decreasing between April and October, because I suppose you're looking there at two things. One, you could put that down to aviation, you could put it down to summer holidays, or you could put it down to, if you think of the seasons and what plants do. And in the winter months, so in the winter months, we're inside, we're burning more, so you're going to have more burning. I'm going to make this shorthand. We're burning more fossil fuels, okay, less burning fossil fuels, and we have less implants. So you have a couple of different reasons, unless anyone can think of anything else. Why do we have this pattern here? This pattern here. Why does the carbon dioxide in the atmosphere drop between April and October? So why are we dropping between April and October? When you think of April to October, it's nice and warm. So I'm putting that backwards, haven't I? That Irish, I was right the first time. That in those months, it's nice and warm out. So it's nice and warm. So if it's nice and warm, we don't need to be burning oil, gas, and coal in our houses. At the same time, I do have that arrow wrong as well. What am I doing? I have more growth in plants. So plants are taking in all this carbon dioxide of the atmosphere, and at the same time, we're not burning loads of fossil fuels in our houses because it's in the summer months. So the carbon dioxide concentration, as you see in the diagram here, can drop right down. And then I'll change the colour of the pen for a second. Then by the time we get to October, all the leaves fall off the plants, so they're not taking in carbon dioxide. And at the same time, we chuck on our heating and get into our cars again, and the carbon dioxide level rises back up for the winter months. Okay. So how could the reason you've given be used as a practical way to slow down and reverse the overall increase in carbon dioxide levels in the atmosphere? So because we're saying it's we're burning less fossil fuels and we've more growth than plants, so this leads to less carbon dioxide, and this leads to less carbon dioxide. So what we need to do to make sure this is an overall increase, so that the graph is always going down, we have two things we could do. Well, we could burn less fossil fuels. So when it comes to winter, instead of burning fossil fuels, we use our solar panels. We use wind energy, we use hydroelectric. Remember all those projects we did? And we plant more trees. So I know it's kind of the same thing over and over again. Okay, moving on nice and quickly because we're taking a long time doing this. 1, 2, 3, and 4. So the first one here, the remains of dead organisms form fuels over a long period of time. So that's going to be number 4. Animals release energy from food and excrete carbon dioxide into the air. It's going to be number 1. Humans burn fossil fuels for energy is number 2. And plants remove carbon dioxide from the air is number 3. Okay. The burning of fossil fuels in the motor leads to excess carbon dioxide in the atmosphere. Okay, same thing. This is more your rising sea levels, exactly the same as we've done before. And then we're on to these kind of questions here now. This is the ones that we were looking at the last day, this endothermic, exothermic job. So is this an example of an endothermic reaction or an exothermic? So do you remember, look, these are cold packs. So this one here is going to be an example of an endothermic reaction. What laboratory instruments could be used to verify your answer? So how do you, anything exothermic, endothermic, you're going to use a thermometer. And this one here, diagram shows an energy profile for reaction that occurs with the two chemicals in the cold pack. And even before, I was wondering, I can't remember, the products here are high, so this is going to be an endothermic reaction. But what they want you to do is show the activation energy. So activation energy, remember, starts down here at the reactants, and it goes up as far as the middle of the curve. So there's your activation energy, your E. Okay. What does the shape of the graph tell you about the relative amounts of energy of the reactants and products? Okay, so what they're saying here, there is that the reactants, bear in mind the y-axis here is your energy. So the reactants, low energy, and the products, high energy. Because the energy is taken in, it got over the hump, and then it goes straight to products. If this curve was to go down further, that energy would be being released as heat or light or something. So that would be mean the reactants or the products are going to be low energy. The reactants are low and the products are going to be high energy, or the products are higher than the reactants. Now, we're going to go on to Adam in a second. This is just something for you to have a look at, give it a shot at home. Bit of a party piece. Someone asked for an experiment to do at home. This is one that I saw on TikTok. Someone showed me this the other day. Take a bottle, fill it with water, leave a space at the top or you will wreck your freezer. Leave a space at the top. Put a lid in it, stick it in the freezer. Take it out when it's almost frozen. Don't let it freeze. Almost frozen. So you should see condensation on the outside of the bottle. When it make sure it's still a liquid and bang it on your counter or your table. See what happens and see, if anyone wants to take a video of themselves doing that and post it and I'll stick it up on the Insta, that'd be cool. You're looking to see what's going to happen and more to the point, why has it happened? So it's quite a cool experiment. Give it a shot. Now, I'm only going to do a small bit of this because there was a lot in that what we just did there. Right, so you'll have a look at this now. This looks like an awful mouthful, right? But it's going to take us a while to get through this. So there's stacks of stuff in here. And what we're going to be looking at this year is having a look at the ratio of atoms. The ratio of atoms in compounds of two elements, right? So it's all about things called ionic bonding and covalent bonding. So don't worry about any of this for the moment. I've kind of done the notes backwards for this. Okay, so you have things like words like valency and that you won't know what they are yet. But I want to jump down here and just go back to what you would have done last year. So all this is the new stuff. There's your periodic table, and have a look at this for today, right? If we get the stuff revised from last year, today we'll be doing well enough. So this is your periodic table here, right? This periodic table, the bedrock of chemistry. And yeah, in the periodic table, you have all these elements. So all of these are elements. An element is essentially an atom. Or an atom is the smallest part of an element that can exist individually. And on the periodic table, they're all numbered. You have number 1, you have number 2, then it goes 3, 4, all the way across here, 5, 6, 7, 8, 9, 10, and then it goes back over here to 11, 12, 13, 14, and so on. Right. And then it goes all the way down, 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 and there's, lots of them. There's a couple of things to remember about the periodic table. We have groups. So if I was to say, here is group 1. And group 1 are these elements like this going across up the top. So they're all elements of group 1. If I was to look for group 2 are all the elements in this column here. After that then, we don't worry about any of this here in junior cert. So we don't need to worry about any of this here at all for the moment. Okay, we then go across and we have group 3, 4, 5, 6, 7, and group 8, or group 0. We can call it group 8, or we can call it group 0, and you're going to see why as we go through this. Okay, the other thing I want you to remember is that the groups are, if the groups go down this way, going across, you have periods. So if we're looking for, say, period 3, period 3 is here, and period 3 goes across. So we have period 1 from the top, so period 3 goes across like that. So the rows going across are periods, and the columns going down are groups. Now all that's going to mean something in a while, right? It'll all start to add up. If you just remember that for now. You've groups going across the top, so the columns are groups and the rows are periods. All those have names. Group 1 is called the alkaline metals. And I know you've done this before, I know you did it last year. Group 2 is the alkaline earth metals. Now you need to remember 4 in total. Group 7 is the halogens. And group 8 are called the noble gases. So they're your 4 things to remember. So your groups are your columns. Your periods are your rows going across, and there's 4 names to remember. Okay, right. Now, what I'm going to do is I'm going to pull out one, right? So I'm going to pull out this one here. I'm just going to get rid of this stuff for a second. I'm going to pull out carbon for a second, right? Right. So let me pull out carbon, this one here. So I'm pulling out the whole square, and I'm bringing it down here. Here's carbon. Now, carbon has a big C, there's your symbol, that's the C, and it has 6, which is your atomic number, and it has a 12 in it, which is your mass number. Okay, so what that means, remember you have 3 subatomic particles, 3 things that make up an atom. If you have a 6, what that means is that carbon has 6 protons and carbon has 6 electrons. Okay, and then we want to figure out how many the third subatomic particle is. So neutrons is our third one. And the way you find out neutrons is you take the big number and minus the small number away from it. So basically carbon is going to have 12 minus 6, which is equal to 6 neutrons. So there are 3 things that we can pull out of any square on the periodic table. Doesn't matter. Any of those, I can pull them down like that, and I can work out these 3 like this. Okay, now I want to draw the Bohr structure of carbon. So the way you do this, now what we're interested in here is we're interested now in this number here, in the 6 electrons. So the way you do it is I take C and I put the C in a nucleus, like so, and I write the amount of electrons in there, like that. And I say, right, I want to fill in my electrons. In the first shell, put my first shell down, and I can put in 2 electrons. The first shell only holds 2. How many electrons have I left? I've already used up 2. I have 6 in total. I have 4 left to put on. So I go 1, 2, 3, 4. And that is the Bohr structure. That's me after drawing out carbon. 6 electrons are in. And the last thing I can do for carbon is I can write the electronic configuration. Electronic configuration is just telling the reader how many electrons are in the first shell and how many electrons are in the second shell. So the electronic configuration for carbon is going to be, well, there's 1, 2 in the first shell, so it's going to be 2, comma, and the second shell is going to have 1, 2, 3, 4. That's the electronic configuration of carbon. I know you would have drawn them last year. It's a first year topic, but I'm just revising it because it's going to be important when we go forward. There is a more drawn out example of what we of how to work it out. They've done argon here. So in argon, the electronic configuration was 288. Okay, so you can see in the diagram there's 1, 2, then there's 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if you think of that now, that argon is 288. The last number in the electronic configuration there is 8. So I'm just going to make a quick link for you. So I go up and find argon on this thing. Where's this big periodic table yoke? Where's argon on that? Aha. It's over here. Here's argon here. And argon is in group 8. Okay. So if it has 8 in its outer shell, like argon has, it's in group 8. Let's go back to the one I drew for a second now. Carbon. Where's my carbon gone? Carbon has 1, 2, 3, 4. The outer shell has 4 electrons. Let's go find carbon. Where's carbon in our periodic table thing? Let's have a look. Oh, here it is, here. And it's in group 4. Okay, I see the connection. So if it has whatever has in its outer shell tells you what group it's in. What about this period thing? Okay, well, let's have a look. What period is carbon in? Let's go all the way across. Carbon is in period 2. And argon is in period 3. So let's have a look at carbon, when we drew. Carbon is in period 2. Okay, so it's in period 2 because it has 2 rings. So 2 rings is period 2. So if that was to stand, we haven't even checked argon yet, but if that was to work for all the elements, that would say argon, because it's in period 3, argon would have 3 rings. Has it got 3 rings? It does. Ring 1, ring 2, ring 3. So there's the connection. Maybe something you didn't do last year. Is that how many electrons it has in its outer shell tells you what group it's in. How many rings it has tells you what period it's in. So if I go up to my periodic table once more, and I'm to pick one of these elements that are miles down. If I'm to pick iodine here, I'll pick iodine, something you've used before, and I don't want to draw out something that has 53 electrons. You know, my arm will get sore and stuff. I don't want to be drawing that out. So what I can figure out, I know straight away, is that because it's in group 7, iodine has 7 electrons on its outer shell, and see, it's going to have 5 shells because it's in period 5. So I can tell a lot without having to draw it out how many electrons it has in its outer shell, and I can tell how many rings it has around with electrons in it. And I've pasted all them in there for you. There's them all drawn out. Loads of different Bohr structures, with some hints for drawing those in your exam. So there's the first 20 drawn out for you, which might help. Small bit more about the history, which I'm sure you've done last year, but a couple of things. If you're thinking of who invented come up with the atom, it was John Dalton, and he came up with this definition, which is important. An atom is the smallest particle of an element that still has the properties of that element. Okay, just a bit of the lingo. You have 3 subatomic particles: protons, neutrons, and electrons, which you remember from last year. And this table is really important in that it tells you, where do you get a proton? Well, a proton's in the nucleus. It has a positive charge, and its mass is 1 unit. Obviously, it's not going to be a kilo or a gram because it's so small. So we call it 1 AMU, we actually call it, as opposed to unit, atomic mass unit. Neutron's the same. Neutron is in the nucleus. It's the same weight as a proton and has no charge. So a neutron is neutral. It doesn't have a charge. This is the funny one. The electron is in the electron cloud or in the rings surrounding the nucleus. It has a really, really small weight. So you'd need 1,840 electrons on a weighing scale to balance even 1 neutron or 1 proton. And its charge is negative. Okay. This is other lingo you saw up top. So atomic and mass units. So 2 definitions. The number of protons in the nucleus is the atomic number. So the small number is how many protons it has. It also tells you how many electrons it has. So if we were to say, right, well, carbon, was the example we took, and it was 612. This is obviously going to be your atomic number, and this is going to be your mass number. The 6 tells us that it has, as it says in the definition there, protons, it has 6 protons, so it has 6 positives in the nucleus. But it also tells us that it has 6 negatives. So if it has 6 protons, it's going to have 6 electrons. If it has 200 protons, it's going to have 200 electrons. The neutrons is the issue. The neutrons, the mass number, the mass number is the number of protons and the number of neutrons. So the way you find that is you take, so if you want to find the number of neutrons, you have to take the small number away from the big number to find it out. And I think I did an example out for you there. So in this one here, I'll just find the amount of neutrons. So see the way it says there, mass number minus atomic number. So in this one here, to find the number of neutrons, for that, you'd have 39 minus 19, which means is going to have 20 neutrons. So this, in potassium, you're going to have 19 protons, 19 electrons, and 20 neutrons. Okay. The periodic table, we went through all these already. The periods are the rows, and the groups are the columns. In groups, they've similar chemical properties. So group 1 are dodgy, sodium, potassium, all those francium, dangerous ones. Group 8 are things like argon and helium, like harmless stuff. Okay, and this just goes through a couple of bits on the different groups. And what I'm going to do is I'm going to start with this on Tuesday in the live lessons. So in Tuesday on the live lessons, what I'd like you to do, if you have a bit of time left today, is to practice drawing a few Bohr structures. So practice drawing a few of these. Make sure you know what is a mass number, what is an atomic number, how do you work out what group they're in, how do you work out what period they're in. This table here is really important. And if we can get that far, what we're going to do on Tuesday is go through the different groups and see, well, how are the properties the same for elements in a particular group. And then we're going to go through the periods and these rules for drawing Bohr structures. And then a bit of new terminology, things like the octet rule, and then going on to the main point, the second year material, which is chemical bonding, ionic and covalent bonding, which can be tricky enough. So what we do is we're going to stop at this point here today because there's an awful lot in there and you've probably forgotten it because I'd imagine you did atomic theory at home. So I'm going to put here. We'll start here on Tuesday. So there won't be a video on Tuesday. I will just go through it with you in person and we'll be drawing out atoms and Bohr structures. And then we're going to say, well, okay, how do we bond them? And how do we stick atoms together? And why would atoms want to be bonded? How do we end up with, if you have the chemical that is responsible for building life, So you have up here you have hydrogen. Over here you have oxygen. They're elements in the periodic table. Well, why on earth then do we end up with H2O? Why would a H bond to another H and bond to an O? So obviously you have something like this, H2O, which is the giver of life, which is the chemical formula for water. But what is it? Why would this want to bond with this? Why would this one want to bond with the oxygen? And that's where we're going to. But we want to make sure that you're okay with the basic atomic theory first. And we go from there the next day. So you have no homework, except what I would ask you to do for the next half an hour is to practice the Bohr structures, as I said. This is a great way to that joins the whole thing together. And the few definitions, and if you want to put some of those into your notes, copy in a summarized form, and then we'll be ready to take it up a gear then going into next week, which will be new material. Right, folks.